Okay, friends, let's talk about how to figure out an empirical formula. So as you can see from this, empirical formulas are chemical formulas showing the simplest ratio of elements in a compound. So we've already seen this in ionic compounds because they always exist as their empirical formula. So for example, when you look at magnesium oxide, magnesium and oxygen have a +2 and a -2 charge respectively. So they cancel out in the lowest ratio and you get MgO. Not Mg2O2, and that's kind of a common mistake that we find when we first learn to balance out charges back in our naming unit. So ionic compounds are already in their lowest ratio. So really, we're going to be talking about some ionic compounds and mostly covalent compounds here. So taking a look down below, we give this nice little flow chart of how to solve and the steps to solve for an empirical formula. We give you some little hints right here in case the numbers don't work out all that nice. So let's take a look down below. Okay, let's chat about empirical formulas. So looking up at the top here, empirical formulas are chemical formulas showing the simplest ratio of elements in a compound. So we've actually already seen this in ionic compounds because they always exist as their empirical formulas. So for example, when you look at magnesium oxide, magnesium has a +2 charge, oxygen has a -2 charge. So the charges cancel out in their lowest ratio, and you write the formula as MgO, not Mg2O2. And sometimes that's a common mistake when we're first learning how to balance out charges way back in our naming unit. So we're going to look at some ionic compounds, but mostly it'll be covalent compounds. So let's take a look below. How do you solve for an empirical formula? So we have a little flow chart here and our steps to figure out what to do first, second, third, fourth, fifth. And then we also have this little table right here, just in case some of our numbers are not exactly whole numbers. Some of you may remember that back at balancing combustion reactions. Sometimes we got a 0.5 for one of our coefficients, or 1/2. We had to multiply the whole thing by 2. So you may see that here as well. So this little box of information just kind of tells us other fractions and what their multiplier should be to make them whole numbers. So there's an example problem down below, and it goes through all the different steps we need to figure out what the empirical formula of the substance is. So let's look at number 1 down below. So it says to determine the empirical formula for a compound that contains 47.27% copper and 52.73% chlorine. So that's from our percent composition. So we're kind of working backwards here. So up above in step 1, it says if you're given percent composition, assume that there's 100-gram total in the sample, because then it takes these percents and it turns them into grams. So really we have 47.27 grams of copper, and we have 52.73 grams of chlorine. So once we've established how many grams of each element we have, then the next step, step number 2, says we need to convert to moles. So I'm going to convert to moles by multiplying 1 mole of copper over its molar mass. When you look on the periodic table, copper weighs 63.55 grams. Same thing for chlorine. Now, normally, 1 mole of chlorine would be diatomic. But here, I don't know what chlorine subscript is going to be. That's the whole point of this. We're figuring out. So we're not going to take diatomic elements into account. So chlorine's molar mass is just going to be 35.45 grams. So when you calculate this, your calculator is going to spit out a bunch of decimal numbers, and we're going to keep as many decimals as we can. Sometimes it's like 3 or 4 past the decimal place. So for copper, we're going to have 0.7438 moles of Cu. And then we're also going to have for chlorine 1.487 moles of chlorine. And the reason why we're going to give a lot of decimal places instead of our normal rounding to 2 decimal places is so that we can see how close these numbers are to whole numbers. It gives us a little bit more accuracy because at this step, step number 3, when you divide by the smallest number of moles, you want to be pretty accurate, right? So if we only gave 2 decimal points for everything, it actually changes our accuracy and therefore changes our final answer. So these problems are really particular. So our rounding rules kind of go out the window. So we're going to look at between copper and chlorine, and we see that copper is the smallest amount of moles. So I'm going to divide by 0.7438. Don't know what's going on with my computer. Divide by 0.7438 for chlorine. And when we do that, I get a 1 for copper. And the closest whole number is going to be really close to 2. So it's going to be super obvious at this step. Either you're going to get close to a whole number or you're going to get close to those decimal places that's like listed up at the top. And think about your fractions, like 1/4, 1/3, 1/2, 2/3, 3/4. So in this step, I don't need a multiplier. So my final answer is going to tell me I am Cu, and I don't need to write the 1 there, Cl2. So this compound is going to be copper 2 chloride. And this is good because in ionic compounds, transition metals, we actually don't know their charge. So we use empirical formulas to help us figure out what the charge is on that copper ion or on that transition metal. And there you have it.